Okay, everyone, welcome to another flux seminar. So today our speaker is Fábio Dominguez. He did his PhD in the Columbia University, working at small x, and actually working on DMDs before they were called that. So afterwards, he moved to Berkeley in Europe for a postdoc and started work on jet quenching. He also was awarded the Matic in 2015. And today, he's one of the leading experts in jet quenching and small x in the community. So it's our pleasure to have you here today. Thank you. And today, we will talk about energy correlators and heavy energy.
Okay. Thanks, Liliana, for the nice introduction. So, what I'm going to talk about is something new that we have been working on in the last year or so, in which we are using a technique that has been gaining a lot of momentum in the PP community in collider experiments, which is this of the energy correlators, which is actually a very simple idea, but it's until now that it's been that it's started to be like really studying and used, and we're the first ones to try to use it in heavy ion collisions and see if what we can do with that, and at least for now we're just doing studies from the theory perspective. We're still waiting for the feedback from experimentalists to see what's going to come out from this. So just let me show you what we got so far. Of course, in the talk we have there are two different things in principle that I need to talk about, which are the energy correlators and the heavy ion collisions itself. So I know this is an audience that maybe not everyone is an expert, so let me again. Okay, so heavy collisions is this sort of experiments right now are being carried out at the LHC and at Drake in the US, where we use the collider, these accelerators, where instead of colliding just protons, we collide the heavy nuclei, typically gold or lead. And in that process, what happens is that this, if you look at it from the lab reference frame, the nuclei look like very contracted in the longitudinal direction, and it's a very dense. The energy density is very high, the collision is very violent, and lots of particles are produced, and it creates a system that then it expands, and it's supposed to thermalize and reach some sort of equilibrium very briefly, which we call the quark-gluon plasma. It's a state in which it's like a deconfined state in which quarks and gluons are free for a very short time, and it's an environment that has a lot of interesting properties, and where we can it's a good laboratory to see some properties to test quantum thermodynamics in such a state. And it's there are lots of interesting questions that you can ask about this sort of system. So this has been going on for I don't know, 20 years now experimentally, and there are different things that in which you can explore this sort of system. And typically there are people look at the collective behavior of like all the bulk or all the soft particles, how that they seem to be well described by hydrodynamics. It looks like this system behaves like a fluid, which is very interesting. But at the same time, we also want to probe the small scale structure and what are the constituents and all this. And what has been done is to make use of hard probes. What happens is that in the initial collision, some of the particles that are created are very hard, are are particles with very high energies, which are going to just go through this plasma and interact with it in some way, and gives us, when we measure those particles, that gives us information about the structure of this system. So in particular, that's what I'm going to talk about those hard probes that are created initially at the moment of the collision, and how they are modified when they go through this sort of medium. So in principle, there are lots of different kinds of particles that you can measure. You can have colorless probes, which do not interact through strong interaction, like photons or Z's and W's, and those are not really modified. Here, what is plotted here is the RAA, which is just a quotient of what you see in a heavy ion collision with what would be the incoherent sum of lots of proton-proton collisions, and the colorless probes are, you get that there's no modification. This is consistent with the heavy ion collision being more or less the same as just a collection of proton-proton collisions. But for hadrons and jets, you do have a suppression, and this is the sort of effect that gives us some information about the strong interactions of these hard probes, right? So this has been interpreted as both depending on what you're looking at, but for hadrons and for jets, it's like these particles, when they're going through the plasma, they lose energy, and therefore the suppression at high PT, the spectrum at high PT is suppressed. So the picture that we usually have in mind is that if you have some sort of collision in which you have two particles going in opposite directions, which fragments creating a bunch of hadrons, that would be the case in a proton-proton collision. But if now you embed this in some sort of quark-gluon plasma, each of these is going to interact with the medium, and that's going to induce additional radiation, which can escape from the jet cone if you're measuring a jet, or if you're just measuring the hadron. Well, the hadron is going to have less energy because it radiated more. And so here's another picture of what it will happen. And the picture that we usually have in mind is like, for example, in this sort of back-to-back events, maybe one of them escapes quickly and doesn't lose a lot of energy, and the fragmentation looks a lot like what you will see just in a proton-proton collision, where you will see in the vacuum. While if the other one goes through a lot of medium, and then it radiates a lot more, and in some cases it can just completely thermalize and disappear in between in the background of all the subparticles that you produce. So the basic principle is that there's a lot of energy loss, and being able to describe that process can give you information about the plasma itself. And the dominant mechanism, especially for light quarks and gluons, that is what is produced the most, is just radiative energy loss, which is just stimulated emissions in this process. You can also have collision energy loss, but that's subdominant with respect to this process, at least for light quarks and gluons. And one of the first signals that was seen in this way is what I was mentioning, that back-to-back jets lose different amounts of energy, and that was actually what was initially done at the very beginning of this, when people were measuring things at Rick, and it was not easy to measure jets. People would just look at the leading hadron in each jet, like the high energy particles, and see that the back-to-back correlations were suppressed with respect to the proton-proton case. So what people, what we theorists did for a long time is just look at what is this medium-induced radiation and how we can come up with calculations based on first principles and see if we can describe the spectrum of emission of a gluon from some parton that undergoes a bunch of different scatterings. Of course, this is from a purely theoretical point of view. This is very interesting, and this is a problem that was tackled in the 90s. But it's qualitatively is very interesting because it's very different from the QED case, in which if you have a very high energy particle, when you assume that the original particle, that energy goes to infinity, all radiation is suppressed because the kicks that it receives from the medium, a particle with a lot of energy almost doesn't feel it. It practically doesn't notice it. But in the QCD case, when you emit something that can also interact with the medium, you can always, no matter how energetic this particle is, you can always emit something soft that it's going to see the medium. So even from a purely theoretical point of view, this is very interesting. Now, the problem, so this is something that has been understood for a while. We have different ways of doing these calculations. But then how you translate this into observables, how you actually use these calculations to compare to data has a lot of problems in the sense that it involves a lot of modeling, right? Because your process is not just this. This is embedded in medium of a particle shower, and there are lots of particles, and emissions come from different places. So all this process of having a clear calculation, a well-defined theoretical calculation from first principles, and the process from there to actually be able to make some sort of prediction for data involves a lots of unknowns and lots of places where you have to just assume some sort of model for the medium. You have to assume that the medium either expands in some way, or there are lots of things that are there that are not under control theoretically. And well, there's been a lot of work in that sense, but just to keep in mind that induces a lot of uncertainties. So if you want to move away from that, then what are the options that you have? So first of all, this idea of looking at how different particles are affected and if they lose energy in different ways was explored for a long time. But of course, if you're looking just at particles, then you have to deal with hadronization and what are the fragmentation functions and a lot of non-perturbative physics that we don't know. So these energy loss calculations, this medium-induced radiation calculations were always thought in that idea of looking at that energy loss. But especially when we start taking data at the LHC and a lot of the experimental side was vastly improved, people start looking at jets because this is something that has been done for a long time in collider experiments. We know that jets are less dependent on non-perturbative physics on the part of the hadronization part and have a lot of nice properties that we can exploit. So then the people started looking also at jets, but then the question of how a jet interacts with the medium instead of just one particle, it's a different question, and there are lots of different things that you have to take into account. For example, if you're just looking at the energy loss calculations, then you typically are looking at processes where sorry, I didn't define this anymore. When I say Z is the fraction of energy, yeah, it is that. It's the fraction of energy taken by the emissions. And in the energy loss calculation, it makes sense that the emitted particle is much softer than the original particle, because otherwise you don't know which one is the particle that you're following. Then the energy loss calculation is only well defined in that limit of very soft radiation. But when you're looking at a full particle shower, then you know that there are some splittings here in the middle that would occur even if there was no medium, but maybe the medium modifies how these splittings happen, and that's that involves a lot of complications. Also, then after you have one of these splittings, then now you have more than one particle, and each of them is going to radiate. But do they radiate in some coherent way, or do they radiate each one separately? And in which cases, it's going to be one way or another. Those are lots of questions that start to be taken into account in this business of jet quenching. And in particular, so people start paying more attention to this sort of how is the modification of those harder splittings, not just like these soft emissions that you assume that there's going to be some energy loss, but also how the inner structure of the jet is modified. So we want to look at jet substructure. So we want to go and look at these hard vertices, take a closer look and see how they what happens when you embed this in a medium, right? So the first kind of calculations coming from this, going in this direction, were these antenna calculations, in which you consider what is the induced emissions from different particles in the same shower coming from a common vertex. And in these calculations, what you start seeing is that the medium can break the coherence between the particles. If you look at this in vacuum, in a Parton shower that comes after a proton-proton collision, you know that the color of all the particles in your shower are going to be correlated, because color is concerned in all these vertices, and it has some specific color state. But if now you have this medium this shower interacting with a medium that is going to receive kicks and is going to change the color of the particles, then you break that coherence, you break those correlations between the colors. And that means that a consequence of that color coherence in vacuum jets is that you have angular ordering emission. You can see the Parton shower as emissions always being always happening with angles that are always smaller than previous emissions, and that is one of the reasons why jets are very collimated. And in the medium, you can break that color coherence and you can break that angular ordering. And then it's a question of and when does that happen? That happens depending on how big is your jet. Qualitatively speaking, if you have a shower that is very narrow, the medium cannot really see the difference between the different particles. And kicks, if I assume something that is, you cannot really see the drawing here, I'm sorry. If you assume particles that are very close together, when the medium interacts with that system, it cannot really tell which of the particles is interacting with. Which means that the whole jet probably the medium, the energy loss from that jet is the same as from just one particle, and the inner structure is not very much changed. But if it happens that your shower maybe there's a bigger angle between the initial splittings, then you can have like two different subjets that interact with the medium separately and can radiate separately. So of course there's a lot of hand waving in this explanation. You can always go and look at it in a more formal way. The calculations for doing this are very complicated, and there are full calculations only like very idealized case in which you assume particles with like almost infinite energy going in straight trajectories and see how they radiate and how diagrams like this interfere, and they can have some destructive interference. But the whole point is that it emerges like a resolution scale, the idea of a resolution scale. If things are very close together, they look like just one particle, but if they separate a little bit, then it looks like you have more sources for this medium-induced radiation. And the question is, how can we see this? How can we make some sort of prediction? How can we notice if a jet is wide enough to do this, and how we can come up with a calculation that actually that actually shows this sort of effects and can at some point be compared to experimental data. So what people came out with is people started borrowing. Well, of course, there have been a lot of ideas here. I'm focusing on only one that has been used a lot recently, and is borrowing this idea that also from the PD community of grooming jets. And the principle is that when you're analyzing these events, you run jet reconstruction algorithm and you find your jets, and then you go and look inside the jets and you decluster the jet and recluster with a new algorithm, but with a procedure that allows you to discard some of the particles, some of the soft particles, and go and look at what is the hard structure of the jet and what is the hardest splitting, and go and look at what is the so more or less get rid of a lot of the soft radiation, and try to reconstruct the actual ordering in which the emissions happen. And in the PP community, they have used this a lot to study jet substructure, and with that properties of different decays or masses of heavy quarks and stuff like that. And it's been very successful. This was originally advertised as the measurement of the splitting function, to be able to see what is the fraction of the energy that takes one of the partons in this hard splitting. And well, it reproduces the Monte Carlos agree very well with the data, and of course a lot more has been done with this. So the heavy community decided to try to do the same. And look for these sort of splittings, but now in a much messier heavy ion environment. And now you have to keep in mind that jets in heavy ions have a lot of additional particles that come from the underlying event, and you always have to use background subtraction techniques, and that makes the whole process a lot more complicated. So the idea was to do the same, use the same grooming procedures, and try to extract what is the angle and the energy fraction of this hardest splitting inside the jet, and then look for the modification of their distributions. And this has been done for what it's called the ZG the CG fraction, which is just go and look at what is the fraction of the energy there. And there's a bunch of different models that, of course, this includes a lot of assumptions and all that, but people have been working on doing these things. But again, you have to keep in mind that because this is a procedure in which you go and look at all the steps in the parton shower, then generalizing this from the vacuum case, like in the vacuum case, you have a lot of like resonation theorems and all that tells you how these parton showers behave. We don't have that in heavy ions, so there are a lot of assumptions that come in when you try to translate that a theoretical calculation into something that you can compare with experiments. And well, there are some promising results in that case, but also some people have noticed that there are some issues with this, and it sort of works for the CG case, but for actually extracting the angular variable, you have more. You have some technical problems that come from misidentification of particles, what are the ones that you actually should count inside your jet, and which ones are part of just the background. So people have been working on this, and people have been proposing to adapt these methods to propose new algorithms that are especially tailored for heavy ion collisions. But this is still some work in progress. But in some qualitative level, we have seen promising results in things like, for example, this plot in which they plot how suppressed are jets for which the angle of that initial emission is either small or big, and jets which have a bigger angle in that hard splitting. are suppressed, have a larger suppression than jets which are more narrow, which goes in the same direction of this sort of arguments in which we were saying that you can, if you have a narrow angle, the medium C is just like a one object, while if you have a larger angle, then the medium sees this as more than one source for radiation. So this is something that lots of people have been working on, but we decided to take a complementary approach and see if something else, in which we don't have to go and look at all the Barton shower, and that's this energy correlator technique. Which the idea is also very simple. We define, so the way that this is defined is through these energy flux operators. So if you imagine that this is like the 4 pi with a collision here in the center, and you go and look at so you're going to have particles flying in all directions, and you define an operator that more or less tells you just what is the energy flow in some particular direction. The formal definition is this in terms of the energy momentum tensor. And yes, if you just look at what is the average of this particular operator in some particular direction, it's just all the sum of all the energies going through that particular element of solid angle. And because this is proportional to, you're not counting particles going through, you're weighting the particles by the energy. That means that the subphysics doesn't count much. It's sort of like removed by the energy weighting. So looking at these sort of operators in this for collider experiments, it's an idea that comes right from 2008. It was developed by Kaufman and Maltesina. And the idea is that if you look at correlations of these operators, you can you sort of have direct access to the cross section of having a particular process. But because it's weighted by the energy, you're like directly looking at these primary vertices that I was discussing before. So here, if you look at the 2-point function, just correlation of two of these operators, this can, of course, this is written in terms of an inclusive cross section. It's very important that it's inclusive. It's not only the probability of producing two particles, but two particles and anything else, whatever. You only fix that you have two particles into particular directions. And of course, there's some, well, here this Q looks like you're not doing anything, you're just dividing at both sides of the equation, but it's important because it's the hard scale of the process, and it's the hard scale which you're supposed to evaluate the cross section. So here it just makes the whole thing dimensionless, but it does play a role when you're evaluating your cross sections. And of course, this is like for two, I can't specify where are these two directions. So the observable that we actually care about is we only care about is what is the relative angle between those directions. And we define this sigma as a function of only that angle theta. Integrated on all directions, so the way that you will measure this in an event is just go and look at all the pairs of particles, and for each pair of particle you weight it by the energy, and you sum over all those pairs that have an unspecific angle between them. So this has been shown. This sort of observables are infrared and collinear safe for n equal 1. But if you go up to if you go up to n equal 2, you can, there are some divergences that can always be reabsorbed, like the way that you will do when you have PDFs and things like that. You can always reabsorb those divergences into what are called track functions. It's a little bit more involved. I won't get into that, but what I want to say is that even though when you go for, you can still go for powers larger than n, and it's still well defined. It's just not strictly infrared and collinear setting. So what we want to look at is something that we can actually calculate. So we say, okay, we want to take, for example, take just one jet. We're not going to look at the whole event. We just reconstruct jets and look at particles inside the jet. And then our R scale is the energy of the jet. And we say, okay, let's assume that it's a quark jet, and try to calculate what is that cross section. So in principle, you're just going to look at the process, just some splitting like this. I just put different colors to emphasize that this can be different representation in general. But if you start with a quark jet, the leading order contribution comes from a quark split into a quark gluon. You could also imagine that there are contributions from measuring quark anti-quark or two gluons, but if you start with a quark initially, those are higher order. Of course, you can calculate them, but let's just start with the leading order. And there's some error involved there in the sense that, yeah, I assume here that the energy, I replace the energy of the two particles by Z and 1 minus C when I divide it by the energy of the jet. So it's like I'm assuming just had one splitting. Of course, that's not going to be the case because these particles have more splitting and have more splittings or can radiate, can lose energy in the medium if I'm in the heavy ion case. So there's also an error from the fact that I'm having more emissions, but that's something that it's under control, and we know how big those errors are. So what happens in the vacuum when you try to calculate this energy correlator? So in the leading order in the vacuum, you're just looking at the big lab splitting functions. So for the case of the quark gluon, we know exactly how that cross section looks at leading order. And if we are just doing this weighted average over the energy fraction Z, that just means that because you always remove this sort of divergences, the sub-divergence when you do the energy weighting, and then that integral just gives you some value. But the important thing is that this correlator goes as a function of just the angle, goes like 1 over theta, which is the usual collinear divergence. Now, what is one of the strong points of these energy correlators is that at least in vacuum you can do a non-perturbative calculation, and you can show there are different techniques that come from conformal field theories, which in this case are in this asymptotic case where you're looking at things at infinity. Then you can still use them for QCD, and you can show that the resummation of these to all orders for small angles, it still looks like a 1 over theta, but now there's an anomalous dimension that you can calculate perturbatively if you want. So what is important about this is that, of course, here I'm just looking at what is the parametric dependence on this theta. There's going to be some normalization depending on the details of the process that you're looking at. The actual value of the correlator is going to be different. But when you plot these correlators against theta, you should see that 1 over theta or small deviations from a 1 over theta behavior. So if you plot this in a logarithmic scale, you either see like you can see the slope of your curves, right? So what that means is that the leading order result is actually very robust, like higher orders, or like whatever happens with non-perturbative stuff, or if you had a quark or a gluon, or if you start with a quark or a gluon, because if you start with a gluon, then this is different, but the 1/θ, so this is still there. Then those ratios that do not really change that power law behavior. So you can see your curve shifting up or down, but the actual shape of the curve should be the same. So this has been studied in that vacuum case right now, mostly by theorists, as far as I understand. And there's a push in where experimentalists are looking at this. But the people who have been looking at this from the theory perspective, they did something that a lot of experimentalists are not very happy with, is that they open data published by CMS, and they took that and analyzed it, and what they see with that open data is that it does look a lot like what you would expect. Like, for example, here in this 2-point energy correlator, this shape of the correlator is precisely that 1/θ dependence that I was talking about. This plot is a little bit different because they multiply by theta, so the 1/θ actually looks like a straight, like an horizontal line is what you see in this region, but you see a lot more in this region. Like, for example, this area here is because you go up to an angle. Here, this R is playing the role of the angle. It's because you go up to an angle where you reach the edge of the jet, and that's why you have this drop here. But then, if you go to very small angles, what happens is that you're reaching. You're going through this transition in which you're looking at very late, where you're really looking at particles that are so close together that the only way that can happen is that they come like from the same. They are just part of the fragmentation. There are like atoms that come from the same particle at the very late stage, which is just hybridization of your partons after the collision, and that's what you see here at very small angles. And this is something that can be calculated, and some people in these papers for it here have done that. And then more recently, there was a paper showing that you can use not the 2-point correlator that I was talking about, but a 3-point correlator to actually measure the mass of the top to a higher accuracy than what you can do now by other techniques. And the way that works is just calculating these correlators, and then when you plot this as a function of the maximum angle between your three particles, you see a bump, and the exact position of that bump is precisely given by the top mass. So this is all very promising. Also, well, I didn't include it here, but these studies are also. People are looking now at what happens when you start with a heavy quark, because there was a recent paper from Alice where they show that they can measure the dead cone effect, where a heavy quark has a minimal angle where it can emit. And this was done by Alice recently, and with some grooming techniques. That is what I explained before, but if you can also do this with energy correlators, and what you see in that case is that this transition occurs farther to the right, or for larger angles, which is that dead cone effect precisely. So what happens when you go to heavy ion collisions? So so first of all, we think that the whole setup gives some advantages, in the sense that in heavy ion collisions you always have a large background from the underlying event, and we expect that background is going to be less of an issue for these correlators, because when you're weighing always by the energies of the particles, you're removing a lot of these soft particles, especially if you look at higher powers of the energies. If instead of weighting things by the energy, you weight it by the energy square, you see that most of the background goes away. And also part of that background is uncorrelated. So it shouldn't, uncorrelated background does not affect the shape of the correlations. It only shifts your curves upward or downward.
You do have a part of the background that is maybe parallel to the jet effects.
Sure.
Does that change the shape in any way?
Yes, it does. But well, people are starting. Well, we're seeing this. People have been looking at what happens when you embed this in some sort of background, and if it is correlated or uncorrelated, or also you can do that with Monte Carlos. And that contribution is the way that you get rid of it is with this trick of using weighting by higher powers of the energy, so you don't keep only the hardest part of the event. All this, that part of the background, even if it is correlated, are subparticles that will not contribute if you work by higher power of information. But yeah, of course, this is all preliminary. We expect that this is going to happen, but until experimentalists actually look at these, and there are more studies with the Monte Carlo generators or whatever, we are not completely certain, right? And the other thing that you have to keep in mind is that this observables is not event by event. What I mean by that is that if you consider one event and you go and look at one jet, you have only so many particles and just a few, some number of pairs that you put in your histogram, and that's it. If you really want to see the shapes that I was talking about, you need to have lots and lots of events and increase the statistics to actually see the shapes. Yeah, so in some sense, it requires some larger statistics. It's not something you can do per event. Like when I was talking before about the grooming, you actually go and look at a jet and you see what is the structure of that jet, and you can say, okay, this jet has a specific opening angle or something like that. That's not something that we're going to do here. For each event, you just collect all the pairs and you throw them all in the bins in your histogram, and that's it. So you cannot use it to tag events like that plot that I was showing, that jets with a higher angle are more suppressed than jets with the smaller angles. You're not going to see that sort of plot here. You're not going to see that sort of effect, which is can be inconvenient, but yeah, this offers other advantages. So, so as I was saying before, at the end, if you want to look at the theory part or how you calculate this, you need to look at this cross section, and that full calculation is very challenging. And we at the beginning I said that we understood more or less well what is the medium-induced radiation, but in the particular limit, which is the soft limit, and we are not interested in the soft limit anymore. We want to know what is the hardest part of the jet and how that behaves. So we need to have a better calculation than that. And also, well, some people have, you can also calculate that C dependence, but if you get rid of the angle, so if you integrate over all angles, you can actually know pretty much have a good description of what is that C distribution, but that's also, again, that's not what we want to do. We want to have an angular variable. We want to know what happens with the angular dependence. So that means that we need to do some extra modeling with this cross section. We have to use other assumptions or approximations, and well, there are two available approximations already in the market. One is just what is called the opacity expansion, is to do calculations as if only you start with the medium only once, which okay, it's easier to calculate, but it has a lot of problems because we always assume that you create a dense medium. That's the sort of case that you want to see, where there's a lot of where the energy density is high, and where you want to look at the effect of multiple scatterings. And this also has unitarity problems, that you can have negative cross sections that for the sublimit are not much of a problem, but for the general case, you start running into those regions much earlier than expected. And well, some people actually have gone a little bit further with this, and have in this paper where they wrote some recursive formulas in which you can actually go beyond n equal 1 and generate orders. But these are complicated, and it's not easy to implement numerically. So okay, so there's still work to be done in that sense. And the other way, that the other available approximation is what we call this semi-hard approximation, which you do resolve multiple scatterings, but you assume that your particles are hard, and in the sense that the scatterings will not deviate much from their trajectories. So you can see under some assumptions, you can actually see some modifications to this splitting, but at the expense of neglecting some effects, some of the broadening effects of these particles. So the approximation that you're using is a little bit restrictive, but this is what we have right now for that actually has multiple scatterings, and that will allow you to see that sort of the correlation for the color of the particles. So that's what we decided to focus on, to use that model. And it has what is nice about this is that it has some very specific characters, some very specific features. So the easiest thing that you can do for this kind of calculation is just assume that the medium is uniform. It has like a uniform density with some fixed length. Of course, this is too simplistic, but this is when you first do it, the calculation works. Then you figure out how to go beyond that, but people know how to do that. And then the structure of the interactions is encoded in some parameter that we call the jet quenching parameter QHAT, which is just like an average momentum transfer per unit length. Again, and we assume that those interactions are more or less up. You have lots of them. And then, well, as a consequence of how the interactions are treated, what you see is that like emissions which have a long formation time, which take a long time to decorrelate from the parent partner, are not really sensitive to the medium. If you have something that takes too long to be emitted, then it emits as a vacuum, because if you're already outside of the medium when you're emitting your particle, then it doesn't see the medium. And it has this effect that I was talking about of destroying color coherence, and it's something that we want to take a look at. So what are these time scales and angular scales that come out of this sort of calculation? So there's a formation time. This is just the formation time in vacuum. It's just it's typically the energy divided by the PT squared, but written in terms of these variables, it looks like this. And this property that I was talking about, of like if the formation time is too long, the formation occurs outside of the medium, is translated into an angular scale that looks like this, and it means that emissions which have an angle that is below this theta L occur outside of the medium and should not see the medium. And then also you can, from the formulas, which I prefer not to show here to not get into too much details, you see this decoherence time, which is written in this way, which is the time that it takes for the pair to actually experience this decorrelation in color, and where you lose the coherence, and where you assume that then the two partons start to can emit independently and can behave independently as if they were not coming from a common vertex. And again, that decoherence time you can translate into an angular scale that is called theta c. And what you know is that emissions that occur with an angle smaller than theta c will just never reach that color decoherence, and the medium does not really see the pair as two different particles. It means that this angle is small. It can be still. The emission can still occur inside the medium, but because the particles are so close together, then the interaction of the medium with those particles are the same as if it was only a single particle, and you don't see much difference. So of course, this theta L is like a stronger constraint of this theta c, in the sense that if you're below theta L, then you should not see the medium. If you're below theta c, you see the medium, but the medium doesn't really resolve the inner structure, but there's still some modification to that emission. So just remember that that's that effect of that critical angle is what I was. This figure was probably not the best choice because it's really hard to see in this light. But is that that theta c is like the distinction between having like only like between having one jet or two subjets inside the same structure. So of course, this is all this is a little bit simplistic with the assumptions that I was saying, but a lot of those assumptions can be relaxed. The reason to do it in this simple setting to begin with is because you can actually see the scales from the actual equations. So then we go and look into this. Well, this I already said this. So if you go and look into this and you calculate the energy correlators in this model, then you have to. I have these plots here where I fix what is the energy of the initial particle, what is the length of the medium, and then I vary the Q hat, which is the strength of the interaction, and we plotted these two different cases where this case where theta L is larger than theta c, then theta c sort of becomes irrelevant, and it only matters as how large your medium is. And in this other case is what we call so this is what we call the totally decoherent case, because anything that is emitted inside the medium, it's already resolved by the medium. But in this case, you can have emissions inside the medium which are not completely resolved. And what you see is that there's these dotted lines at the vacuum, and then your lines are on top of the vacuum until some initial angle, and that is the effect that I was mentioning of below some angle. You should not see any modification with respect to the vacuum, and then once you separate from the vacuum, just changing how strong the interactions are, change a little bit the shape of your curve. But you see that the changes in the two cases are different. Here is like you see that the slope here increases when I'm increasing this Q hat, but then in this case is like that slope has already saturated, and increasing the Q hat is just moving this peak, the peak in the distribution further to the right. And so while we look at the features that we look in these curves, is this, well, I forgot to say this here is it's just the difference between a normalized difference between the medium case and the vacuum case, just to look at the different features of the curve. And what we see is that there's something that we call an onset angle, which is where the effect starts. And there's some that doesn't depend on the value of Q hat, it just depends on how large the medium. And then there's this peak angle, is something that we cannot really say how much is the peak angle from the equations from the model, but it's a clear feature that we can extract from these curves, and we can see how it varies. Now we see that the variation of that peak angle is very different in these two cases. Here, like the peak it almost doesn't move when you change the skew path, while here it just keeps moving to the right. So it's something that can tell us something of the difference between these two different cases. So what we just did was just to run this for a bunch of different sets of parameters and look at what are the onset angle and the peak angle and perform some fits. We noticed that for the onset angle, it doesn't really matter in which region, in which case you are. It always scales like this variable theta L, the theta L that we said before. And then, but for the peak angle, the fits are very different depending on which case you are. And that actually we put it in this plot where what we actually put is the ratio. We chose this ratio, this particular ratio, just because it highlights what we want to show, but it removes some dependence of the variables of the peak angle that are already there. And what we see is that when you plot this as a function of the energy of the jet, you see a change when you go from one region to the other region, from the region where things are always resolved to the region where things are not necessarily resolved. So by looking at those features of the shape of the correlators, you see that you reproduce some of the things that were present in the model for the first section, right? So what the message that I want to convey here is that, of course, we use a model that was very simplistic and that can be improved in many ways, and we're already working on that. But what we want to highlight is the fact that the features the features of the calculations, the fact that you can identify that these different scales, these different angular variables appear in the observable. You can see that you can then extract things from the result, and whatever you put in your calculation is going to show up in the observable. That's not trivial when you're doing heavy items, because for example, when people started studying energy loss calculations, well, sure, maybe you have a very detailed calculation at the partonic level, but then when you embed this in something in some more complicated, when you go and look at how that energy loss happens for a long trajectory, and you have to resum things and all that, what you realize is that you get very similar results when you change your model. So whatever is the characteristic of the model that you use for the interaction is not that relevant when you go and compute the observables. But here we're seeing that the features of the calculation really show up in the observables, which is something that is interesting when you are going to compare different models. And what is interesting is that this seems to work well in terms of an angular variable that at least in heavy ion collisions had not been present before. It's the possibility of really defining in terms of an angle, which is what we want to see for these decoherence effects, which is something that people have been looking at for a while in the heavy ion community. So just did something. Okay, so of course, so this is just the beginning, and there are so many things that you can do. So you can improve the model for the medium splitting. You can consider expanding media. You can look at heavy quarks. Okay, this is outdated. I'm sorry, this already came up. So, and you can use it for Monte Carlo studies. So there are many things that should be done with this, and there's going to be a lot of progress in this also from the experimental side. So, that's it. Thank you.